So now we're going to take a look at effect size. So effect size, the terms measure of association and effect size both mean the same thing. We're quantifying the relationship between two groups. It's more common to talk about effect size in the medical field when you want to know how exposure is related to disease. What effect does exposure have on disease outcome? On the other hand, measure of association is used as an informal way to measure the same thing, quantifying relationships between two groups. In most other fields, measures of association can be referred to specific tests for relationships, like the chi-squared test that you had a look at in the first year. So we had a look at the chi-squared test as a measure of association. We were seeing if there was a relationship between the two groups that we were looking at. For example, the colour of the snail and the location that the snail was found. And we were having a look if there was a relationship between those two. So we're going to have a look at a more scientific version of this, which is effect size. And as it says here, it's usually used in the medical field. So this is one that if you're going on to study something biology related or science related, that you're going to come across the most. So the effect size is how large an effect of something is. Most statistical research includes a p-value. It can tell you which treatment process or other investigation is statistically more sound than the alternative. But while a p-value can be a strong indicator of which choice is more effective, it tells you practically nothing else. And we've seen the p-value come up in the binomial hypothesis testing and the normal hypothesis testing that we looked at last year. And we've seen it come up on the graphical calculator in other areas such as the 2-sample T, 2-sample normal hypothesis testing. So effect size can tell you how large the difference between two groups is, the absolute effect, so the difference between the average outcomes of each group, and the standardized effect size is for an outcome. So effect size is an important effect sizes are important to allow the layperson, which is someone who isn't a statistician, to be able to understand the results of your analysis. And that's really important because if you think about what actually happens when we have, let's say, medical data, is that then doctors are having to explain the difference between one drug and its effectiveness and a different drug that performs the same action. So we need to be careful in the fact that this needs to be interpretable. The one that we're going to look at for effect size, we're only going to look at one test. There is more than one test, but this is the most commonly used one, is Cohen's d. So Cohen's d is the most common way of measuring effect size. An effect size is how large the effect something is. For example, medicine A is better effect than medicine B. So the formula, and this is given in the formula booklet, looks something like this. In your formula booklet, it does look slightly different. This comes up on page 7 of your formula booklet. And on page 7, it appears as x bar 1 minus x bar 2 over S. Looking at it in this form, M1 is the mean of group 1, M2 is the mean of group 2, and S pooled is the pooled standard deviation. Now, if you remember when we were looking at the 2-sample t-test, we had a look at pooling the standard deviation there. So this part here underneath our square root sign, that is the same formula that we were used to find the pooled variance in the two sample t-test. So this formula is again written on page 7 underneath the Cohen's d formula, and it appears exactly like this, that S equals this, but it is the same formula as we do to find the variance, but of course, because this is the standard deviation, we are square rooting it. So all of this is on page 7 of our formula booklet. So Cohen's d works best when we have a large sample size, and in this case we're saying the large sample size is more than 50, which is different to what we have said before. For smaller sample size, it tends to overinflate the result. So that can sometimes be a comment that we can make on the effectiveness of having a look at the effect size. So if, for example, we have done a t-test, when we're then having a look at the effect size, because t-test is only done on a small amount of data, then we might end up saying that it may be overinflated due to the small sample size. A correction factor is available which reduces the effect size for smaller samples by a few percentage points. However, this is not covered in the course. So Cohen's d, we end up having a value for d. So a d of 1 indicates that the two groups differ by 1 standard deviation. A d of 2 means that they differ by 2 standard deviations, and so on. So the standard deviations are equivalent to a z-score. So 1 standard deviation is 1 z-score. We have a couple of rules of thumb when we are interpreting our d value. And these you do have to remember. They are given to us specifically from the exam board, so you need to remember these intervals. So if it is between 0.2 and 0.5, we call this a small effect size. If it's between 0.5 and 0.8, we call this a medium effect size. And if it is greater or equal to 0.8, then we say it is a large effect size. So having a larger d means that it has a larger difference between them. And therefore we have a larger effect size. Our test is more sound. So we're going to have a look at an example. So we've got the alkalinity in milligrams per litre of water in the upper reaches of a river in a particular region is known to be normally distributed with a standard deviation of 10. The alkalinity readings in the lower reaches of the river in the same region are known to be normally distributed with a standard deviation of 25. 10 alkalinity readings are made in the upper reaches of the river and 15 are made in the lower reaches of the river. So we've got our data here. So to start off with, we're investigating at a 1% significance level the claim that the true mean alkalinity of the water in the lower reaches is greater than the upper reaches. So this question may seem quite familiar to you. So I'm only going to do the hypothesis test quite quickly, because in the initial part of the question, we were given the population standard deviation for both the lower and the upper reaches of the river. That means that this is going to be a 2-sample normal test. So we're going to have H0 mu u equals mu L. H1 means mu u is going to be, we want the alkalinity in the water in the lower reaches to be greater. So we want mu u to be lower than mu L. Remember that you have to define these symbols. So mu u is the population mean alkalinity level in the upper reaches, and mu L is going to be the population mean alkalinity alkalinity level in the lower reaches. As we had with our 2 sample normal before, we're going to write a little summary about what we know. Mu U, mu L. Well, we know from the original introduction that the upper reaches has a standard deviation of 10. So upper has a standard deviation of 10. Lower has a standard deviation of 25. Then we need to put the data into our calculator to be able to find the sample mean. So this is just a recap. It could just give you some summary statistics and ask you to find the Cohen's d value. It could be a part B of a question where you've had to do a hypothesis test in the first part, as we are doing here, and then it's asking you to find the effect size in the second part. So calc, check your set. It needs to say list 1 because that's where we put our data. We don't have any frequencies, so that's just going to say 1. And then we click on 1 var, which gives us a mean in the upper reaches of 80.5, and the number piece of data that we have in the upper reaches is 10. Again, putting in the data for the lower reaches, and then we're going to find the mean for the lower reaches as well. And again, double check that you have entered all the data in correctly. We are going to be using these values again later on, so it's extra important that we get them correct now. Which gives us a mean in the lower reaches of 99, and the number piece of data in the lower reaches is 15. So remember, for a 2 sample normal test, we're using the formula that's on page 6. Ignoring the part on the top that we don't use means that we will have 80.5 minus 99 divided by the square root of 10 squared over 10 plus 25 squared over 15. That gives us Z. Remember that you could have done it the other way around on the top. I think when we did this example before, I did do it the other way around. So minus 99 divided by the square root of 10 squared over 10 plus 25 squared over 15. So this gives us a test statistic of minus 2.57. So the size of the test statistic would be 2.57. Remember, for the critical value, you're going to use inverse normal. So back into the stats part of our calculator, dist norm inverse normal. Remember to always have the tail going to the right. Because it's one-tailed, we're going to keep the area the same. Remember, if it was a 2-tailed test, we would halve the area there. And we're using the standard normal distribution. So we're saying the standard deviation is 1 and the mean is 0. So that gives us a critical value of 2.33, to 3 significant figures. So then, as our test statistic is bigger than the critical value, we're going to be rejecting H0 at a 1% significance level. There is sufficient evidence to suggest the mean alkalinity level is greater in the lower reaches than the upper. So for part B, we need to start off by having a look at our S, because the D formula for finding the value of Cohen's D involves the S. So S is going to be the square root of the number of pieces of data that we have in our first group, so 10 minus 1 times that standard deviation squared, plus the number of pieces of data in our second group, minus 1 times that standard deviation squared, divided by the number of pieces of data in the first group, plus the number of pieces of data in the second group, minus 2. So we're going to put this into our calculator, so we need to go into the normal part of our calculator. And this would give us the square root of fraction 10 minus 1 times 10 squared plus 15 minus 1 times 25 squared divided by 10 plus 15 minus 2. And this gives us an S of 20.48329118. And we want to keep the whole number because we are going to do another calculation with it. So then D is going to be the mean from the first group, so that's 80.5, minus the mean from the second group, so that was 99, divided by RS, or RS pooled. So you could do the takeaway on the top the other way around, that would be fine. So we've got 80.5 minus 99 divided by our pooled standard deviation, which was the last thing I had in my calculator, so I can just use answer, which gives me minus 0.903. I can round that to 3 significant figures. Remember, it's the size of that we are taking into account when we are doing our comment. So remember, more than 0.8, we say it's a large effect size. But we could also add a comment saying this may be overinflated due to small sample size, because we only had 10 pieces of data in one group and 15 pieces of data in the other group. So moving on to the second example, we've got Mr. Brown is the owner of a large bakery in a large town. He believes that the smell of fresh baking will encourage customers to purchase bread. To investigate the belief, he records the daily sales on 10 days when the window is open and 10 days when the window is shut. The following sales in pounds are recorded. Assuming that this data may be deemed to be a random sample from normal populations with the same variance, investigate the baker's belief. So we don't have paired data, we only have 2 samples of data. It doesn't tell us what the population standard deviation is, so it's going to be the 2 sample t-test this time. So for A, we're going to have H0 mu open equals mu closed. H1, so he believes that the smell is going to encourage customers to purchase this. So we're saying that mu open is going to be more than mu closed. So where mu O is the population mean sales when window is open. And mu C is going to be the population mean sales when the window is closed. So then we have to find the information that we need. So we're going to have mu O and mu C. So in our calculator, in the stat part, we're going to delete anything that we already have in there. Type in our values first of all for open. So 202, 204.5, 207, 215.5, 190.8, 215.6, 208.8, 187.8, 204.1, 185.7. Again, double check that you've entered those values correctly into your calculator. Then we're going into calc, check that your set says list 1-1, which it should do from before, and then 1 var. So the sample mean for when it's open is 202.18. Our sample standard deviation when it's open is 10.7577155. And the number of pieces of data that we have is 10. Then we're going to delete the data and we're going to enter the data for when the window is closed. So we're going to have 193.5, 192.2, 199.4, 177.6, 205.4, 200.6, 181.8, 169.2, 172.2 and 192.8. One var again, so that gives us a sample mean for when it's closed of 188.47. Sample standard deviation when it's closed is 12.5161273. And the number of pieces of data for when it's closed is 10. So remember, for the 2 sample t, we start off by doing SP squared, which is n minus 1 times the standard deviation squared, plus n minus 1 times the other standard deviation squared, divided by the number of pieces of data in the first group plus the number of pieces of data in the second group minus 2. So back into the normal part of our calculator, we have 10 minus 1 times 10.7577155 squared plus 10 minus 1 times 12.516123 squared divided by 10 plus 10 minus 2, which gives us 136.1909427. Then to find our test statistic, our t-value, we're going to be doing 202.18 minus 188.47 divided by the square root of our SP squared, so our 136.1909427, times 1 over the number of pieces of data in the first group plus 1 over the number of pieces of data in the second group. Remember that formula is also on page 6. So in our calculator, we will have 202.18 minus 188.47 divided by the square root of our SP squared, which we already have, times 1 over 10 plus 1 over 10. Which gives us a test statistic of 2.63. The degrees of freedom is going to be 10 plus 10 minus 2, which is 18. When we're looking up our critical value, this is a one-tailed test. Doesn't tell us what significance level to use, so we're going to use a 5% significance level. So then on page 19, we're looking down from 0.95, because it's one-tailed test, we don't half it, down to 18, which gives us a critical value of 1.734. So then as our test statistic is bigger than the critical value, we reject H0 at a 5% significance level. There is sufficient evidence to suggest the mean sales is higher when the window is open than closed. So for part B, we're finding the Cohen's D and we're commenting on the effect size. Now, luckily, remember first to find your S, which is going to be the square root of 10 minus 1 times 10.7577155 squared plus 10 minus 1 times 12.5161 273 squared. Even though those are only the sample standard deviations, because those are the standard deviations that we have used in the hypothesis test, those are the ones that we need to use. So if you've ended up using the sample standard deviations in the hypothesis test, you need to use those when you're finding the effect size. Otherwise, you're using data that wasn't actually being used in your hypothesis test. Now, we have actually already figured this out, so all I'm going to do is square root the value that I got for SP squared here, so 136.1909427, just to save myself a little bit of time, which gives me a standard deviation of 11.67008752. Then when we're finding D, we're doing the mean from the first group, so 202.18 minus the mean from the second group, divided by our S pooled, or just our S. Putting that in our calculator, so 202.18 minus 118.47 divided by our pooled standard deviation gives us a whopping 7.17. So this is a very large effect size. But again, this is going to be inflated due to the small sample size. So remember, it needs to be more than 50 for you to be able to say that it was a large sample size. Now, I'd like you to try the Now You Try question, answering the hypothesis test and then finding the Cohen's D. So hopefully you paused the video and you gave the Now You Try question a go. So here we have a school mathematics teacher decides to test the effect of using an educational computer package consisting of geometric design and illustrations to teach geometry. Since the package is expensive, the teacher wishes to determine whether using the package will result in an improvement in the pupil's understanding of the topic. The teacher randomly assigns pupils to two groups. The control group receives the standard lessons and the experimental group using the new package. The pupils are selected in pairs of equal mathematical ability, with one from each pair assigned randomly to the control group and the other to the experimental group. On completion of the topic, the pupils are given a test to measure their understanding. The results percentage marks are shown in the tables. Then we have our table there with our pair, our control person's percentage and our experimental person's percentage. So then for part A, which I've done in red here, we're assuming that the percentage marks to be normally distributed investigate the claim that the educational computer package produces an improvement in pupils' understanding of geometry. So our H0 is that the mean of the control group equals the mean of the experimental group, so mu C equals mu E. And H1 we've got mu C is less than mu E, where mu C is the population mean percentage mark of the control group and mu E is the population mean percentage mark of the experimental group. So then I did the control group minus the experimental group, and you can see this in my calculator in the stat part. In list 1 I have the control group's values, in list 2 I had the experimental people's values, and then in list 3 we went up to the top, highlighted where it says list 3, then did list 1 minus list 2, and that gave us our differences, which are now in list 3. Then we had to find the mean of the differences, the sample standard deviation of the differences, and the number of pieces of data. So we had to go and change our set. So it was looking at list 3. 1 var, and we have minus 1.5, 5.72033441, and the number of pieces of data is 10. Remember, it's fine to end up with a negative mean, you just can't end up with a negative standard deviation. So then we were going into test T1 sample. We don't have any values in it, and our hypothesis test symbol goes this way. So we've got symbol 0, and then we've got our minus 1.5, our 5.72033441, number of pieces of data 10, which gave us our test statistic of minus 0.29. So the size of our test statistic is 0.29. Remember, for the paired t-test, it's the number of pieces of data minus 1. So 10 minus 1 gives us 9. So then it doesn't give us a significance level to use. So we're using a 5% significance level. We don't have to half it or anything because it's not two-tailed. So looking down from 0.95, across from 9, which gives us 1.833. That's looking up on page 19 again. So then, as the size of the test statistic is smaller than the critical value, we accept H0 at 5% significance level. There is insufficient evidence to suggest that the mean percentage score is higher with the software, when the software is used than without. So for part B, we have to calculate the Cohen's d and therefore the effect size of the test and comment on the value. Now this time we didn't explicitly find the mean for the first group and the standard deviation for the first group and same for the second group, but luckily I already have the values in my calculator. So all I have to do is change my calc so that it's looking at list 1. And then I wrote down those values for my control group. Then again changing the set so it's looking at list 2. And then writing down those values for my experimental group. Then we had to find the pooled standard deviation, so the square root of 10 minus 1 times 12.4257796 squared, plus 10 minus 1 times 3299 squared, all divided by 10 plus 10 minus 2. And remember, the whole thing there is square rooted. So then you can see, if I go up in the normal part of my calculator, I've got this part typed in here. Then I've square rooted it, which gave me 10.59795574. Then to find the Cohen's d, we're doing the means from each, so 80.2 minus 81.7. divided by our pooled standard deviation, which gave us minus 0.142. So the size of our effect size is 0.142, which is a very small effect size. It's even less than the 0.2. We need to say it's only got a small effect size. So I've given some examples there, and you've tried a question where we're having to do a hypothesis test first, and then the part B is asking us to find the effect size. But like I said, they could just give you some information and then ask you to find the effect size from that. Make sure you use the standard deviation that was used in the hypothesis test. Make sure that it's clear what you are putting in your calculator. And then make sure that you always write down an interpretation. If you have small samples like we do here, remember that can overinflate our effect size, and it's better to find the effect size with larger samples, and we're classing a large sample in this case as being more than 50, not more than 30, which we've come across before with the normal distribution. Thank you very much for listening.